Hi everybody, Mr. Trophy here again. We're going to pick back up with our Chapter 3 notes and continuing on talking about our normal distribution. So let's take a look at what in general, what a normal distribution looks like. We can see normal is the same thing as saying we've got that symmetric distribution where we have that mean in the middle, and then off to the sides there we have all the other values of our sample or our population that become increasingly less likely the further away that we get from the mean. So it gives us that nice symmetric bell-shaped curve here. And with our normal distribution, typically when we graph them, we're going to graph them all the same way, where we've got in the middle here, we've got our mean, or sometimes we can say this is the number of standard deviations away from the mean, which is going to be 0. So we can do either one of those numbers there. And then from there, we're going to graph some vertical lines, which just represent our standard deviations. And we want to try and make them evenly spaced because they represent the same distance away from the mean in each time. So, for example, this first line, we're going to say this is 1 standard deviation away from our mean. Second line is 2 standard deviations away from our mean. And our third is 3 standard deviations. And we typically will only go to 3 when we're graphing our normal distributions. Past 3, it becomes usually unnecessary to do so because it's very unlikely stuff occurs past 3, but we'll talk about that in a little bit. Similarly, we're going to go towards the left-hand side here. 1 standard deviation below the mean, 2 standard deviations below the mean, and 3 standard deviations below the mean here. And the really nice thing about these normal distributions is that no matter what you're graphing, we're going to get the same percentage of observations that fall within these groups. So 1 standard deviation above the mean is going to be 34% of our data. From 1 to 2 in that group here, this is going to be 13.5%. From 2 to 3, we've got 2.35%. And then from 3 and above, really tiny, 0.15%. And then since our graph is symmetrical here, we can copy everything down to the left-hand side as well. It's going to be the same. Now, these percentages aren't exactly spot on, but they're very close to what it does fall into in actuality. A lot of times in stats classes, we use these percentages here because they're much easier to work with. So in actuality, instead of 34%, this would be 34.13. This is 13.59. But we use these nice rounded numbers because they're much easier to work with. And for the purposes of our class, that's what we're going to stick with here. So now let's talk about what the normal curve actually is, and that is the probability distribution curve of a normal random sample. So all of that, even though we haven't talked about it in a while, should be somewhat familiar to you all. So it's just saying, or it's in a pictorial example of how likely observations are to fall when we're talking about a normal random sample. And a couple of examples of things that are normally distributed. So if we look at a general population, height is normally distributed. So is blood pressure. IQ is also normally distributed. And something a little more familiar is coming up, or maybe a lot of you have probably already taken these, SAT scores. Normally distributed. That's just a couple of real-life examples when we see this normal distribution and that type of curve pop up in real life. Let's try and make one of these on our own here. So we've got the scores of a stats test are normally distributed with a mean of 82.5 and a standard deviation of 3.1. Let's draw the normal curve to model this situation. Let's start off with our axis here. And these are a little tricky to draw, but just do your best. Now with the peak of our curve, that's going to be our median here. So we can label that as our mean value, or 85.2. And then we're told our standard deviation is 3.1. So we just need to plot 3 standard deviations above and below our mean here. So we're just going to add 3.1 to our mean several times. We add 3.1 to 85.2 and we'll get 88.3. Then we'll add another 3.1, get 91.4. And our third standard deviation is 95.4. Now similarly, if we're talking about below the mean here, we're just going to subtract 3.1 from our mean. So we've got 82.1, subtract another 3.1, we get 79 for 2 standard deviations away. And then for our 3 standard deviations away, we are 75.9 there. And usually when you make these, I'm going to ask that you label those percentages in here just so we can see how likely each of these are to occur. So we got 34%, 13.5%, 2.35%, and 0.15%. And that's going to get mirrored on the left-hand side again. Let's do a couple more examples of these though. So the empirical rule, that's what I was mentioning earlier, where we have those kind of where we use those rounded decimals to get easier answers to work with, and that gives us this empirical rule, the 68, 95, 99.7, which are some really easy numbers to work with, and that just refers to the probability that an observation falls within one of our given standard deviations. So I'm going to draw out our standard deviations again. 3 above, 3 below. And let's take a look at that last page. We had 34% could fall between our mean and our first standard deviation above and also below. So from 1 standard deviation below to above in that group there, we get that 34 plus 34, giving us 68% of observations fall within 1 standard deviation away from the mean. So in that first group here, 68% of all of our observations are going to lie somewhere in between our 1 standard deviation away from our mean. And I should label these. Let's say that's our mean, 1 standard deviation, 2 standard deviations, 3 standard deviations, and then same thing on the left-hand side. So similarly, if we're looking for 2 standard deviations away, all the way from 2 below to 2 above within this group, we're just going to add up everything that fell into these 4 smaller groups, which is going to give us 95%. So 95% of our data falls within 2 standard deviations of our mean. And then our last one, our third group here, is including everything except for our little endpoints here, which adds up to 99.7% of our total observations. So that's why we typically only look at 3 standard deviations away from the mean. These 2 groups on the outside make up 0.3% of all the observations. So it's really likely that stuff is going to fall within those 3 standard deviations away from our mean.